So in 7.5, we start dealing with conditional probability and independent events, because up to this point, a lot of the situations that we looked at were independent, which means that one event is not going to affect another event. But now we have to consider the fact that, depending on how we're doing certain situations, if we're picking people from a crowd, that's going to be dependent because, if I'm saying I'm picking 3 people to do a task and, each person has kind of put back into the mix, that, theoretically I could pick the same person all 3 times and say that's 3 different people, which is kind of absurd. So situations like that, and there's other situations where assuming independence is, not very likely. So we have to take into consideration, things not being independent at times, and we have to be able to accommodate if they are independent versus if they are dependent. So 2 formulas that they kind of give you here in some new notation. When you see that vertical bar, that means the probability of B given that A has already occurred is actually equal to the probability of both A and B occurring divided by the probability of A. Now, under most circumstances, if the events are independent, then the probability of B and the probability of B given that A has occurred would be the same. So when I have this product rule down here, the probability of A and B equals the probability of A times the probability of B given that A occurred. For independent events, that probability of B given that A occurred is just going to be the probability of B. So you may see that formula from time to time as well, but they will qualify it and say it's independent. The product rule, though, is going to be that formula because that actually relates how you would compute that in every situation, whether it's independent or dependent. So for example 1 here, and we actually did some situations in class where we kind of looked at these kind of circumstances before. 2 cards are drawn without replacement from a well-shuffled deck of 52 playing cards. And again, we're assuming that you all know what playing cards are, that there's 4 suits, face cards, ace through 10 are your non-face cards. Jack, kings, and queens are your face cards. We're not including jokers here. So things like that. And so you're asked these questions here. What's the probability that the first card drawn is a heart? Because now we're picking 2 cards out of this. What is the probability that the second card drawn is a heart, given that the first card drawn was not a heart? And C, what is the probability that the second card drawn is a heart, given that the first card drawn was a heart? So consider these and answer the questions in Play Pause It, and then we'll go over this. Okay, so hearts. The probability of the first card is a heart. So we're picking 2 cards. We're saying, okay, when I pick my first card, what's the probability that that first card drawn would be a heart? Well, hearts are basically one of the 4 suits in a deck of cards. So I can look at it, 13 out of the 52, or basically just 1/4. It's 1 suit out of the 4 that's on cards. So the probability of getting a heart would be 1/4. Now we're focusing our attention on the second card, but we're going to be also being asked to consider something happened with the first card as we do it. So for part B, it says, what is the probability that the second card drawn is a heart, given that the first card drawn was not a heart? So we're not looking for the probability that the second card, or that in particular, just the second card, being a heart. It's the second one being a heart, given that the first card was not a heart. Well, assuming that we picked a card beforehand, and it was not a heart, that means that 1, I'm going to only have 51 cards left. But I'm going to have all the hearts left to pick from, which means all 13 of them. So the probability of me picking a heart on the second pick, given that the first pick was not a heart, would be 13 out of 51. And for part C, the probability that the second card drawn is a heart, given that the first card drawn was a heart. Well, now, when I consider that, well, the first card drawn being a heart means that I picked one of the 13 hearts out of the 52 card deck, so now there's 51 cards left, and there's only 12 hearts left. So that would be a 12 out of 51 for the probability of getting a heart, given that the first card was a heart. So that's an example of how to handle the given that situation. For example 2 here, some backwards working and maybe some diagrams will help you with this one. The probability that a battery will last 10 hours or more is 0.8. The probability that it will last 15 hours or more is 0.15. Given that the battery has lasted 10 hours, find the probability that it will last 15 hours or more. So I want you to take a moment, figure out what that probability is, and then we'll go over this. Okay, so the thing we have to kind of keep in mind here is that the batteries that last 15 hours or more are going to be a subset of those that lasted 10 hours or more. I mean, they have to have lasted at least 10 hours for them to even make it close to the chance of being 15 hours or more. So it is going to be a subset. So to kind of put a better spin on this, I'm going to draw a diagram to assist me. And so my diagram, so what I have are 3 regions. I have my universal, I have one circle or ellipse, another ellipse. The centermost ellipse is those who are lasting 15 or more hours. And from that, we were told its probability for that is 0.15. For those that are lasting 10 or more, it's supposed to be 0.8 in total, but that includes those who are going to last 15 or more hours. So I got to take that 0.15 out of there when I adjust for this. And so I'm going to have 0.65 that are in the region where they last 10 or more hours, but they don't quite make it to 15 hours. They would fall short of 15 hours. And then you would have the 35% or 0.35 that fall outside of this group. So now what they're saying in this problem is, given that the battery has lasted 10 hours. So basically, we're already throwing this group out because we've already made it past that group. So given that the battery has lasted at least 10 hours, find the probability it will last 15 hours or more. So out of that 0.8, 80%, because 0.15 of them are going to last, 15 hours or more. So I would just basically do 0.15 out of 0.8, which is 3/16, which is 0.1875, or about 18.75%, if you want to do it as a percentage. As I mentioned before, they mentioned independent events, because one of the things you always have to look at, we talked about mutually exclusive. Those are things you have to consider, like whether or not both happening at the same time can actually occur. Well, independence versus dependent, because sometimes you may have a situation where one event does not have an immediate effect on the other, and there's other cases where they are going to have one effect on each other. So when they talk about independent events, they are mentioning that the probability of A given B is just going to be the probability of A. The probability of B given A is just going to be the probability of B, because A and B have no effect on each other. They're independent. And when I go to the formula down here, they say test for the independence of 2 events. If I find out that if I do the probability of A and B, and I calculate it, if I know what that is, and I do probability of A times probability of B, if they're the same thing, then I know that the events are independent of each other. Because sometimes I might have a circumstance where I think they might be dependent, but the data shows otherwise. One does not affect the other. Whereas if there is some sort of difference, then that means that there is some dependence, and I have to sometimes adjust for that. Independence of more than 2 events. So basically, again, if I want to know if 2 events are, more than 2 events are independent, then I would need to figure out what the probability of all of those events occurring at the same time are, and then I would take the probability of each individual event and multiply them together and see if I get the same thing. So consider this. An experiment consists of two independent trials. So you're told off the bat they are independent. So, so basically in trial 1, you could get two different circumstances. You get A or B, that's it. And they tell you what the probabilities of each one of those occurring are. And there's two outcomes in the second trial. You can either get C or D. Now, I'm not saying what these things are. They want you to draw a tree diagram representing this experiment and use this diagram to find these. Tell you though, honestly, you don't really need the tree diagram to answer these questions to a certain degree. But, because a lot of these are easily handled by the formulas that we have and that we've mentioned already. So, because a lot of these have been given outright. So, but the tree diagram should definitely agree with it. So, you are asked to draw a tree diagram. We'll look and see about that in a moment. But find these probabilities, whether you use a tree diagram or not, and then we'll go over this. Okay, so from the information that we're given in this problem, we're told that the probability of A is 0.4, the probability of B is 0.6, the probability of C is 0.3, and the probability of D is 0.7. So when I look at this, I mean, to ask the question, what's the probability of A? Well, that just came right out, and that's 0.4. That's all it is. I'm going to look at B and D at the same time because we are dealing with independent trials. Now within the trial, the events might be. I mean, I would say A and B are probably not independent because it's only one could occur, or those are the two possible outcomes. If A occurs, then B's probably not going to occur. That's dependence. But whatever the two trials are independent. So if I say, okay, the probability of C occurring given that A occurred, those are two different trials that are independent of each other. And since those are two different trials that are independent of each other, then the probability of C given A and the probability of C are going to be the exact same thing. They're both going to be 0.3. So it doesn't matter if A occurred or not. The probability of C occurring is going to be 0.3. And therefore, the probability of A and C is just going to be me multiplying the probability of A times the probability of C together. Although I could say the probability of C given A still, that's still what the formula that they have us use. But remember, the probability of C given A is the probability of C. So in any case, I get 0.12 for the probability. So pretty easy question that a lot of students overlook. So be careful with things like this, that you don't overlook clear definitions and things along those lines, because that can certainly cause problems down the line. And on to our last example. A box contains 2 defective Christmas tree lights that have been inadvertently mixed with 8 non-defective lights. If the lights are selected one at a time without replacement and tested until both defective lights are found, what is the probability that both defective lights will be found after 3 trials? So take a moment or two and look this over and figure out a probability of this, and then we'll go over it together. Okay, so what gets challenging about this is because of the circumstances that you're asked to do this, and knowing some logic about how you would go about doing such a test the way they're describing. Because a lot of students would try to go back to some of those combination methods and find out that it really doesn't produce the answer that we're looking for here. Because the combination method, basically, the best I could possibly do is say, okay, well, I'm only going to pick 3, and I want to see the probability of me getting both defects and one non-defect. Well, the thing is, if I pick the 2 defects at first, I'm not going to pick a third one. That would be silly. But this one here is saying that, what's the probability that it's found after the 3 trials are done, after I've tested 3 bulbs, basically. So basically, for that one there, I have to assume that I didn't get a situation where, I picked the 2 defects on the first 2 picks, because it would be pointless to pick any others after that. After I found my 2 defects, I know that at that point I found them all. So I have to look for 2 very specific instances where I have 2 defects and 1 non-defect out of 3. So when I look for the probability that both defects are found after the 3rd pick, which is what I'm looking for here, I have to assume that, well, I'm looking for the probability of me picking a defect on the first time I pick, a not defective light, and then a defective light to get my 3rd one. I have to assume that the 3rd one chosen is defective. But I've also found the other defective one in one of the first 2 trials. And then along with that, the other possibility is for me to have picked a non-defective light the first time, and then picked a defective light the second and 3rd time. So these are the 2 circumstances I have that, would combine together would give me the overall probability of me picking both of the defective lights out of this mixture of 10 lights, by the 3rd pick. So when I figure out these probabilities, now I'm going to get a lot of the same numbers in the numerator and numbers in the denominator, just associated with different, mixtures of them. But as I look here, well, me getting the probability of me picking a defective light of the first pick would be 2 tenths. Then the probability of me picking a not defective light would be 8 out of 9. And then the probability that the 3rd one is defective would be 1 out of 8. And then coupled with that, the probability of me picking a non-defective light on the first pick is 8 out of 10. The probability of me picking a defective light on the second pick, given I've already picked the first one, I did my first pick, would be 2 out of 9. And of course, the probability of me getting a defective light on the 3rd pick would be 1 out of 8. So I would basically add these 2 together. I would do some simplification first. And I would basically get 1 out of 45 plus 1 out of 45, which is 2 out of 45, which is 0.0 repeating 4s. So about 4.44% chance of this occurring under the description given. So more to be considered with this one, because one of the things that when we do those combinations and permutations, we're under the impression that each person had an equal chance of being picked. This one here, likelihoods are not always going to be independent of each other. So I had to kind of be careful and assume, that I had to go about different routes of dealing with these problems. But that's the last example for this. If you have any further questions, please make sure to bring them up in class. Until next time, have a good day.